Oh, okay, okay. The next one?
Yeah.
Okay, good. Yeah, so this is more or less the outline. When I am talking about the genesis, it is not the genesis of the problem, it is the genesis, the way we came across to the problem. Okay, so it is mainly that, and that's the way I go ahead. Actually, we are working on a, let me put it this way, in a related problem for quite some time. It is not that that's a reason that you will see I have a huge number of collaborators. I was working on a similar problem, but this particular specific problem we came across recently, which has its own difficulty. So we thought this one that let me look at it, and I think some of the solutions are, at least from the statistical point of view, definitely it has more meaning. Okay. So what I will do, I will try to first build up that from where it came. I mean, rather, let me put it this way again. I mean, the way we have seen the problem, the way we have come out to this problem, and it basically came out. We can look at this problem. We came out from the one-dimensional model, and this one is a typically two-dimensional one. So I'll first explain about what are the things we have seen in the one-dimensional one, and then we'll see that the problem what we are dealing with. The problem is very simple to describe. It is if you have a periodic data, okay, you have a periodic data in the one dimensions, and you are trying to analyze the periodic data. That's it. And you see the periodic data, I think, in all the time in today's life, every day. I mean, looking at the number of today's ECG data, blah blah blah. All of them are periodic. Okay. Actually, you can see the periodicity even in the higher dimension also, and that's what our interest is. Two things. I mean, what is a periodic data, and why do you care to analyze? I mean, why do you bother to analyze the periodic data? Well, I am not going to give a formal definition, but I think all of us know, all of us at least feel about it. It is basically that if you are looking at the one dimension, it is kind of a repeated pattern. It's a periodic pattern. I mean, you see this one that it repeats after a certain time. It has a formal definition. Let's not go into it, but we know this one that it has a repetitions. Similarly, if you're looking at the higher dimensions, 2 dimensions or the 2 or 3 dimensions, if you're looking at it, it has a symmetric pattern. Okay, it has a symmetric both in the well, that is a, whenever I am talking about the higher dimensions, it basically means that it's a colored data. So there is a symmetric pattern in the 2 or the 3 dimensions. The first question is, well, why do you care to analyze? Of course, I mean, it's a mathematical curiosity, no doubt about it. That's what that is the first thing, for the theoretical reason, and there is a huge amount of work it has been done, mainly looking at from the theoretical point of view. Of course, it has been applied in the to get this many things out of it, and there are 2, I think, main applications if you are trying to look at the periodic data. One is the prediction, and another is the compressions. And the prediction, I think we can always see this one, that because it's a periodic data, it repeats. So clearly, you want to predict in the future, and we'll see some of the examples why it is important. And when you are talking about the data compression, and I think in today's world it is becoming more and more relevant. And I'll just give you 1 or 2 small examples. The data compressions, and suppose I'll show you the picture also. A simple thing, suppose you are looking at, say, ECG data or the EEG data. They are periodic in nature. Suppose you have a very good model about those things. So then if you want to record all those ECG or the EEG data, you don't have to keep the whole data set. Okay, you can forget about the data set. If you have a good model, you can just keep few parameters. So that's the way you can compress the data significantly, and that is important, because if you are looking at any of the first world countries now, I mean, particularly all these Scandinavian countries, the way they are keeping the health records and all these things, and they have a data they may be monitoring every month or every 6 months for the whole population. Okay, so now think about it. storing all the data, it's an enormous task. Okay, so in that case, if you have a good data compression technique, you can gain, you can achieve quite a bit. Okay, so these are the different applications which are there. This is one of the very famous data, which is the what is this? It is all available in the website. I mean, in the net. This is called this is called this US Airlines data, and you can see that in this particular case, definitely prediction is an important thing. I mean, you have this data till today, you want to predict it for the next 1 year or the next 2 years or the next 5 years. Definitely prediction is an important aspect in this particular one. Okay. Similarly, this is one of the example. Again, this is also available in the net. This is this brightness of the variable star. I think it has been collected in Australia, one of those astronomical lab, where they looking at the how the star moves, and that's the way they have this brightness they have collected. Again, the prediction is an important thing. This is a vowel sound which is there, it is not that one. Yeah, so this is one of the data set, again the periodic data, which is important, that if you want to compress the data. Okay, that is definitely an important thing. Okay, this is one which we got interested, which is in the higher dimensions, not in one dimension. It's a higher dimension. It's a Newton's rings. They are actually, I mean, that's what we got interested when you move from the one dimension to 2 dimension. This is again, it's a nice periodic data. There are a lot. I mean, you have these texture data which are being used extensively in the material science. So you have this anyway. So all these things are there. Yeah. Okay. So let's look at the basic formulation. It's a very simple. That's the way we can start. We are trying to looking at the periodic data. So we are simply looking at the sine and the cosine function. That's it. That's a standard way. So any periodic function, I mean, sorry, I should not say any periodic function. I mean, this a cosine omega t plus b sine omega t, it gives a nice periodic function. Go one step further. You are trying to look at any periodic function. So the natural thing is the Fourier expansion. Okay, so we know this one, that for any periodic function, I should be able to do this Fourier expansion, and which is an infinite expansion. So yt is equal to this one. That's a very standard one. So so this is the way we're looking at any periodic functions. Okay, well, what happens this one? Well, I mean, we can get back all those AKs and BKs, which is very easily. I can get back this one. This comes from the standard Fourier expansion. But what happens this one? I mean, when we are coming to the real life, I mean, that's what the statistician comes into picture. That when you are looking at the periodic signal, of course, you may not observe exactly the periodic signal. What is going to happen? You are always going to observe. You are going to observe with some noise. Okay, that's what it is, and that's what it is. You have this term xt, which is there, which is a noise component. So what you observe basically the yt's. You have those periodic signal which is sitting there, but associated with it, you have this plus xt. So that's the way you have this. You have your signal there. Okay. Unfortunately, what happened this one, that you have infinitely many parameters. If you try to looking at in the previous one, that's the reason this one, that it's a very common practice, and it makes sense also that we basically truncate it. We truncate it up to a certain point. K is equal to 1 to up to p. Where do you want to truncate? How do you want to truncate? Those things are different problem, but you make this truncation k is equal to 1 to up to p, but you also make some kind of a generalizations. Instead of omega, you are bringing it. Yes.
Do you know why, and you want to understand what is AK, BK and X, or on the other hand, do you know AK, BK and X? You want to find
No, we only know yt's. You only know yt's. That's the one what you observe. That's the one. I will put it that way. I only know yt's.
So you want to construct AK, BK?
I want to construct my signal, which is my this quantity.
Okay.
I want to yes.
Omega
K and p, as well as p also sometimes.
P, but X is a function. Capital X.
X is a random variable. X is a noise. X is a noise. So I know this one, that
Oh, you know capital X?
No, I do not know. I do not know the exact value of the capital X, but I know it. I know that. Suppose I know that it's a Gaussian one. Gaussian one with mean 0 and variance something. Absolutely, absolutely, absolutely. So I know this. I know this xt in the sense that I know its form, in the sense that I know that it's a Gaussian noise maybe. Okay, they are all independent and all these things, or it may have certain structure.
How do you show this noise is additive?
Well, I'll come back to this one. Yes, I think that's a very good one. How do you know that the model is additive? That's the assumption what you make at the first time. That's the first thing, and I'll come back to this one, and then you cross verify whether the assumptions is correct or not. If it is not, you have to go back. Yes, that's what I'll come back. Yes, exactly. So
frequency of this time period also changes.
what is that?
The frequency of this time series,
Yes,
that is also changing.
that is omega case. It is omega k is changing with respect to, which is different than the previous one. There the omegas were fixed, and we are trying to chop it off at the point up to the point p instead of looking at the infinite one. So we are compromising there, but at the same time we are making it more flexible because of this omega case.
So one technical very
Yeah.
one very technical
Yeah.
question. So when you do that,
Huh.
you are using the this series should converge. So it is pointwise convergence or something you are using.
Well, I mean, this series should converge in the sense that is not a very difficult to show. Of course, what is saying this one, that if your AKs and BKs are bounded, it is fine. See, in the sense convergence in what? Because your P is a fixed quantity. Suppose the P is equal to say 10. Your P is a fixed quantity. Your YT is, you can see this one that will be.
As long as it is not an infinite series, convergence.
That's the thing. That's the thing, because we are chopping it off at the point P. Okay, we are chopping it off at the point P because two reasons. As one point, what you are saying about the convergence problem. Second point is that as a statistician, I can look at it and see this. Well, I won't be able to estimate all those infinitely many parameters because I'll be always observing a finite number of data points. Okay, even if it's a large one, I'll be observing finite number of data points. It's okay, fine. Okay, so that's what it is. So I'll come back to that. I'll come back to Sagar's question also. Yes, that is an important thing. How do you know that? We'll see. We'll see how we are looking at that. Okay. So well, there are two things. One is the deterministic component, which is sitting at the beginning, and which is everything is constant there. There is no randomness, and there is a random component there. So how do you do? Okay. As I said, I mean, I have that what I observe. I always observe this YT, which is the signal plus the noise YT, and I am trying to extract the signal out of it. That is my ultimate aim. From the data point, finite number of data point YT is equal to T is equal to Y1, Y2, Yn. From this data point, I am trying to extract those muties. That is my aim. Well, so this is basically, that's what we have. I mean, I think that is one of the major difference. The way statisticians handle the thing and not statistician handle the thing, because we try to estimate xt also in some way. Okay, and I will show that why it is important. Okay, it is not that just the estimating the signal components, which is the P, A1, A2, AP, B1, B2, BP, and the omegas. It is not only estimating that one is important. Of course, that is important, but at the same time, it is important to estimate the noise component also. It is important to estimate the noise component also xt. It is not that the value wise, it is not that I am trying to estimate x1, x2 like this. Say for example, suppose I am assuming this one that it's a Gaussian noise, I am trying to estimate the variance, okay, or I am using some other noise, I am trying to estimate the corresponding parameters. That is important, okay, and you'll see that the reason why it is important.
So what it amounts to is somehow loosely like random noise inflicted Fourier series.
Absolutely. Nothing else. It is absolutely true. But the only difference is that there are two differences. The Fourier series is your infinite one. The second one, the frequencies are changing here. So there are two different things. Yes, your omega 1, omega 2, omega p. You have a p different omegas. Where if you're looking at in your Fourier series, your omegas is fixed throughout. You have an infinite.
Why we learn more than one omega here?
See, that's a compromise. See, because we are making the compromise on the number of components, we are, instead of looking at the infinity, I am making it the number of components to be fixed.
Your omega is a function of p.
Omega is a omega. Yes, I have omega 1, omega 2, omega p. Yes, exactly. You can take it as a.
You fix p and you get 1 omega.
I have a p different omegas.
Is it a linear function of p? Is it a linear function of p?
No, I have basically just p different point and p different. I mean points on this one. I mean it is a function of p in the sense.
P different values.
Absolutely, p different values. I have a p is equal to say 5, then I have omega 1, omega 2, omega 5. That's it. Yeah. So yeah.
So estimating xt as in the distribution of xt.
Distribution of
So
xt.
there should be some sort, like there's a sense of infinity there also, because ideally you need all movements, right? Like if you know nothing about the distribution.
No. So it is not that. No, I'm not coming from there. What I'm doing is, suppose I am assuming it is, for example, say Gaussian one or the Laplacian one.
So that is a cutoff also.
That is the assumption first I am making it. Okay, I do all the things. Okay, that's what I am coming it now. Okay, and let's see. I mean, let me just see this one. Yes, I think this is the one. So that's what you do. That first we assume certain structure on xt. Okay, I mean when you have the data, we assume certain structure on xt, and then based on that structure, I mean I'll come up with an estimator and I'll find out my the mean vector, this mu t, the signal I mu t. At the same time, I estimate the error also based on that assumption, because I have assumed certain structure on xt, and then I'll come back and I'll find out this xt. Then I verify the assumptions. Okay, because now I try to verify the assumptions, that whether my assumptions are correct or not. Okay, my assumption correct or not. If the assumption is satisfied, then it's fine. I mean everything in. I mean the assumption actually here is even whether it's additive error or not. That also I can cross check. Okay, and if it is not, then I have to go back and I have to change the assumptions.
Verifying assumption means you want to somehow statistical estimator like 1 sigma level, 2 sigma level or something.
Not only that, whether these additive assumptions whether it is satisfying or not. Okay, whether the additive assumption is satisfying or not. Whether, say for example, I am making the assumption that it's a Gaussian one, whether it's satisfying or not. So those are the assumptions I will be testing.
Is there any relation between the values of k and random mass?
Values of?
K, so k is equal to 1 to 5, p.
Well, for the time being, what I am saying this one, that I will be observing a fixed number of sample size, say for example, say 1000. So I'll be observing y1, y2, y1000. So now whatever I am saying it based on that sample. Okay, clear? So based on that sample, I am doing all these things. I will first making an assumption on the structure on the xt. I'll go for the estimations. I'll cross check this one. I'll estimate the error. I'll cross check that one. If it is satisfying, I am happy. If it is not, then I'll go back. I'll go back and I have to change that assumption. Okay, so that's the procedure what we follow. Okay, so let's look at some of the simple estimation procedure, or I would say simple, some of the standard estimation procedure, what is being used for the one-dimensional case. One of the very standard one which is being used, I think majority of the people, which is the periodogram estimator, and I think particularly it is being used extensively by the electrical engineers, and so periodogram estimator, which is nothing but so because this is the one which you know completely, your yt's are completely known to you. So you are looking at a new function which is your I theta, which has these two quantities. So natural question is, why are you looking at that quantity? What does it reveal? Okay, so let's look at a simple example. What I am looking at, I am just looking at two components. You can see that this is my A1 B1 and this is my A2 B2. So I have two component model. Omega is 0.2 pi, omega 1, and my omega 2 is 0.5 pi. So these are the two omegas, and this is my error xt, and I am simply taking it to be Gaussian error with mean 0 and variance half. Okay, I am taking it very simple one. So you can see that I have my A1 B1, both of them are 3, my A2 B2, both of them are 3, and my omega 1 is 0.2 pi and my omega 2 is 0.5 pi. Okay, and now if I plot this I theta, what I have, so I have a simple line, this one. So that basically you can see this one, that these are the two places where I am getting two peaks, which are nothing but your 0.2 pi and 0.5 pi. So it is basically you have the two peaks at the point omega 1 and omega 2. So it is one of the very, very nice way, simple way to looking at that I theta function and see this one where the maximum is, and you try to find out some numerical procedure to extract that where the maximum is. So that looks like a very, very nice, interesting one, and we can give it a try. Okay, but not always we are that lucky. So if we can just change slightly, if we are looking at again the same model, I am just changing my A1 B1, I am keeping it same, I have no change here. Omega 1 I am keeping it same, I am not changing. My A2 B2 I had changed. A2 B2 I am changing from this 3 to 0.25. Basically I have reduced the amplitudes, and you can see that my omega 2, which is 0.5 pi, and so omega 2 is everything is same except the second amplitudes. Instead of 3 I have reduced it to 0.25, and I have changed my variance. The Gaussian error I have kept it fixed, but I have changed the variance 2.0. Instead of half I am making it 2, which is basically 4 times, and now everything got changed. So now if I plot this I theta, you cannot see the second component at all. You cannot see the second component at all. You can only see the first one.
So what does I theta, what was the physical meaning of I theta?
I theta, you can, as I say this one, that, yeah. So this is the I theta.
So what does it contain?
That is precisely I am trying to show it in the picture. That is precisely what I am trying to show it in the picture, that well, if you have this yt in the first one, you can see that this I theta picks up the two peaks. Okay, there, even if I have the original signal has two different frequencies, but it cannot pick it up. Your I theta cannot pick it up. So that means your I theta is actually very, very sensitive in that sense about the variance of the noise component. If the noise component as well as the amplitude of the noise component also. Okay, so because if you look at it, because in the first case I have the amplitude of the first one is fine, amplitude of the second one is 3, it is able to pick it up. Okay, it is able to pick it up both the peaks, but on the other hand, if you are looking at the second one where the amplitude is much lower, 0.25, and amplitude is much lower, and it is not able to pick it up. Actually, to be a little bit, if you are looking at this quantity, let me just put it here. If you are looking at the length, this length is nothing but proportional to A1 square plus A2 B1 square, amplitude square. Okay, what is happening this one in the second case, because your A1 square plus A2 square plus B2 square is much smaller, and that's the reason that it is not able to detect. That's what is happening. Okay, so although the I theta in the ideal situation looks very nice, but not in all the time.
But I theta is like the power spectrum.
Absolutely, nothing else. No, I'm just putting it that way. Yes, it is a power spectrum.
Originally, your YT has
Yeah.
this to be whatever your
Absolutely. But the power spectrum is not able to pick it up if your amplitude is less. If the amplitude of one of the frequencies is less, it's not able to pick it up. That's what is happening.
But in that case, Gaussian noise you changed to the second one.
Second one, the variability I have increased.
You are increasing.
I have
That
increased.
doesn't matter.
Of course, it has matters, and that's the reason this one that it makes all the things more worse. Okay, say for example, if you do not have any Gaussian, say for example, if you put that to be 0, you'll be able to see two peaks. You'll be able to see two peaks. But if you put the variance there, if you put the variability there, it very difficult to make. See, another thing, even if the two of them are very close to each other also, if your omega 1 and omega 2 are very close to each other, then also you are not able to pick it up. That problem is also there. Yes, please. Mu t is the first one. See, in this particular case, your mu t is this quantity. Mu t is this quantity, the original signal. That's one. See, because other than if you take it out to your error, rest of the things is mu t. Okay, fine. Yeah, there are some of the two components. Okay, fine.
If it has 3 components, like
Same thing. Exactly the same
but
thing.
then if there is a hierarchy, things fails. The amplitude, there is a hierarchy. Like
No. If there is a hierarchy in the amplitude, it is not going to fail, not necessarily. Say for example, suppose I have a 3 component. Suppose say first amplitude say 5. second amplitude may be 4, third amplitude may be 3, and the variance is half, you will be able to pick it up. You will be able to pick it up all of them. There is a hierarchy, you will be able to pick it up all of them. But the problem, all these things are happening because it is not only the hierarchy, but how much more it is. Okay, so for example, suppose the first one is 5 and the second one is say maybe 0.1, you may not be able to pick it up. That's what is going to happen. And as well as at the same time your variability is also more, you may not be able to pick it up.
So a priori, if your original data has 3 or 4 peaks, you see it and accordingly you are fixing it.
But you do not know. I mean, say even if say for example, suppose even if say in this case, even if you know a priori there are 2, which one you are going to pick it up? Okay, even if you a priori know that there are 2 frequencies in the signal, which one it should be? It is not. It is not very clear. How do you do that one? Okay, it depends on many things. It depends on many things. It depends on the amplitudes. Depends on the how close they are. It depends on the variability and all these things. Okay, fine. All right. Yeah. So what is the one of the what is the remedy? I mean, we go back to our usual classical one, the least square estimator. I mean, there is no other way. But you looking at the difference of yt minus this quantity, you try to maximize, try to minimize that quantity, and that's a standard way, and it works. Okay, it works in the sense it works theoretically very well. Okay, but it is not true. There are several problems. It's a highly nonlinear problem. Okay, the least square surface has several local minima. Most of the time, I think that is another major issue. Most of the time, the Newton-Raphson algorithm may not converge. Okay, I mean the standard algorithm, if you may not converge, even if they converge, it often converges in the local one compared to the global one. Okay, and the problem becomes much more complicated if your number of component is large, if P is large.
Newton-Raphson always goes to the, depending on the way you are starting.
Of course. Yeah. So here the problem all the more difficult because it has several local maximum, and not only local minimum rather. I mean, in this case, because they are trying to minimize. Not only it has lots of local minimum. You know that how close you should choose your initial guesses also. Okay, and that makes it an extremely difficult one. And just to give some kind of a flavor that how the problem is a very, very important one, and how complicated or how difficult it is. There is a paper which is almost like around 25 years back. There are several algorithms which has been proposed, and that particular paper which came out in actually one of the good journal in signal processing, they have only the list of references. I have never seen any paper which just gives a list of references which try to solve this problem, and which has more than 300 references. Just the list of references. It is not a review paper. It is just the list of references he has given it, which is 25. Yeah, I mean, and he's one of the.
So there was one thing in the last transparency you showed y minus. So this should be ideally the lowest compound.
That is precisely. I am trying to minimize it. That's it. Yes, I am trying to minimize that one.
You get this, you will get that x.
Absolutely. So basically, I mean, if you do all these things in a perfect manner, actually this gives an estimate of your xt also. Exactly. That's what it is. That's what we do. That's what it is.
It will ideally not converge to 0.
Definitely not. No, definitely not. In fact, it can be shown this one that if you're looking at the Gaussian error, if you take an average of that, after minimizations, actually it will converge to the variance.
What is here?
N is the sample size. That yt t is equal. That's the sample size I had taken. Y1, y2, yn. That's the sample size I had taken it. Sorry, I think both of them capital. Sorry, it should be capital N. That should be capital N. I mean, let's put this one is smaller. Yeah. Yeah. Same. Sorry for that. Yeah. Yes. How do I construct this? No. See, that's the thing. No? That's what I'm trying to do. So I'm looking at this quantity. And so I have to minimize with respect to A1, A2, AP, B1, B2, BP, and omega 1, omega 2, omega p. Yes, I mean that's the way I am going to get the estimates. So you can see that I have basically 3p parameters. So suppose you can see this one, that suppose even if your p is equal to say 5, okay, so you have basically 15 parameters to estimate to minimize that quantity. So you can see that it is a 15-dimensional optimization problem. Okay, even if p is equal to 5, it's a 15-dimensional optimization problem. That's what it happens. And that's the reason that it makes it a numerically also a challenging problem. Okay, fine. Okay, so that.
Binning is a problem.
What is it?
The binning, like how you put the data in the different bin, is that a problem?
You mean that no, because I am looking at the data as a time series data, so I have this y1, y2, yn. So I mean, yeah, so those are the fixed one. No, I did not get your question maybe.
No, if you are just looking at some data samples,
yes.
you put the data number, like when you change the binning, like the sample number also changes in that particular bin. Right?
No, okay. Let me put it this way. I mean, what we assume that I have my fixed sample size for the time being, and I observe the data y1, y2, yn. So now my problem starts from there.
So you know y1, y2, y3. So when you
y1, y2, yn. y1, y2, yn.
So but when you try to minimize that, you
Yes.
also require to know AK and BK.
No. That is those are the parameters I'll get. See, only thing I have these yi's. That is the only thing I have. That is the one.
Then the program will try to minimize it.
Exactly. The problem is to minimize this particular quantity. I treat this whole quantity as a function.
Is it solvable? There are so many parameters.
Yeah, I mean, that's what. that's the reason I said this one, that even 25 years back the paper came out which gives
I understood the problem now.
yes.
I understood that.
Yeah, no, that's what I'm saying. I mean, that's the reason that I'm saying this one. It's a challenging problem, but it's an important problem. So that's the reason that people came out with lots of meta-heuristic solution also. So this is the ideal one. Okay, so this is the ideal solution because you can prove theoretically this gives you the best estimate in some sense. I'll come back to that. Okay, so that's the reason that is precisely the reason when I say this one that there are so many papers, that means people came out with the meta-heuristic algorithm. That's what it is. They do not want to try to solve this one. They do not want to try to solve this one because, as exactly what you have said, is it solvable? That's the first thing which comes to your mind. I mean, not only that, I mean, just think about it. Suppose your p is equal to say 100, which actually happens. Suppose you are looking at an ECG data, actually p turns out to be very, very large. So maybe around 75, 80, something like that. Your n is also quite large. N might be 1000 because you can have enough amount of data for the ECG signal. Okay, you have enough amount of.
So the machine will churn out various AKs and omega k's and try to.
Well, I mean, machine, if you give them the proper algorithm, I mean, that's what it is. I mean, yeah, I mean, well, nowadays everybody said, oh, I will be using the machine learning model. I mean, I don't know what they do, but yes, I mean, yeah. So just let me just try to convince Kaushik first, then I'll come back. Yes? Okay.
Immense difficulty of what we are doing.
Okay. Yeah. Now, please, yeah.
Why are you keeping the parameter that's there in the noise? For example, you have taken the Gaussian. I could have taken the variance as a parameter which will be used in the optimization.
How will it help? No, I'm not getting. See, okay, let me try to see. I mean, whether what I'm saying. Whenever I am saying this one, what I say that, well, I am assuming this one that my YT, which is in the form of there is a certain deterministic component, which is a signal part, and there is certain noise component, and the noise component I am getting it because whenever you'll be observing the data, you'll be getting some noise from somewhere. As Sagar was asking that why it is additive noise, yes, that I can cross check later on. But first I will make that assumption, a simple assumption. Yes, suppose I make that assumption that noise is additive here. Based on that assumptions, I am coming up to this.
I was asking because you gave two examples.
Yes.
When you changed the
variability, yes.
Why can I not use that also in this optimization together with this 3D data, 3D parameters?
How will you do it? I did not get. I mean, how we are going to do that one? See, what you are saying, what you are actually we will be capturing that after this. If we can solve this problem, I will capture actually what is my error variance, sigma square.
I think what he's saying is that you want to fit a data set to YT.
Yes.
So this plus the noise also has a characteristic. So these are the characteristics of the signal.
Absolutely.
Plus the noise also has a parameter.
Absolutely.
Can we include that in the least?
Actually, if that is the, okay. All right. Oh, very good one. Yeah. See, it's not going to make any difference because, particularly if you assume this one as a Gaussian noise, you can see this one that you can separate it out. Okay, so you can separate it out in the sense, I mean, all of you know about the maximum likelihood estimator. So actually, you can do it in two stages. One thing is that you can estimate this parameter first, minimizing this one, and then you can estimate the variance. That's what I said. Actually, both of them, we are doing it together because that, yes, exactly. I mean, I did not get, yes, actually, we are doing both of them together, but you can separate it out in this particular case based on the assumption that it's a Gaussian error. Okay, fine? Yeah, good. Okay. So that's what it is. Okay. So that is the difficulty of the problem, as we can see. And as I said that, well, the problem becomes, it's a higher dimensional problem. It becomes. So that's one of the solution is that let's not do this one in a complete manner. Let's do it sequentially. That means we do one at a time. The natural question is, how it is possible? Why it is possible? It is possible because they are orthogonal. They are orthogonal in nature. Those components, at least asymptotically, they are orthogonal in nature. So actually, you can do it sequentially. The nice part is that both of them has the same accuracy. That means the sequential estimator and the overall estimator. Theoretically, it can be shown that both of them has the same accuracy. So as you can see that now it looks like a solvable one, because even if say p is equal to 100, I do not have to solve 300 dimensional optimization problem. I will be solving only 100 one-dimensional problem. So which becomes much easier, which I can do it very easily. Okay. So I'll be doing one at a time. I'll be taking out, and then I'll be taking out that first component and go on like this.
But here also you have A, B and omega 3.
Of course, yeah. See, no, actually, well, I'm putting it this way. Actually, this particular problem can be converted to a one-dimensional optimization problem. That's a simple one. That's not a very big.
But you have only one omega.
See, because each time you'll be getting one omega at a time. See, this is the first one. This is basically turns out to be the omega 1. Then once you take it out, this one, then you replace your y by y tilde, then you'll be getting omega 2 and so on. It's an iterative process. Okay, but the thing is that you do it sequentially, and then you'll be getting all the things. Okay, but it is a much more doable one compared to the previous one, and that's what it shows that, well, instead of solving 100-dimensional optimization problem, I'll be solving 101-dimensional optimization problem, which is becoming definitely much easier. And in fact, as I said, it happens actually in case of the ECG data and all these things. We need to solve maybe 75-dimensional and things like that, which is doable. Okay. Well, there is another. This is another one which is a very, I would say counterintuitive, but it works very nicely. If you are looking at this, the neat adaptation algorithm in general, which is a very simple one, which is basically like this. This is the gradient and this is the Hessian. That's what we have, but that does not work. But on the other hand, if you have a step factor, of course, this 1/4, it does not come from heaven. It comes from the by theoretically it can be shown that with this step factor modification, actually it gives the very good result. Not only theoretically it can be shown, it not only produces the estimator, which is, in fact, it is better than the least square estimator in terms of the variance. Okay, so
can we generalize this also for maybe hundreds of nonlinear equations? Like if
we do Newton-Raphson,
Uh-huh.
sometimes they are not converging.
Yes.
But how this 1/4?
No. See, let me put it this way. This is step factor modification is there in the Newton-Raphson. It is not there. But it depends on the nonlinear problem. Say this 1/4, it has been obtained just because in this specific case, using this special structure of this nonlinear function. So if you have a separate nonlinear function, you have to work it out and see whether you can get any step factor or not. So it is not that in general for any nonlinear function it is like that. No, it is not that, but it is. Okay.
And to continue just
Yes, please. Yeah.
clarification. So when you are making your 100-dimensional optimizing problem in 101-dimensional problem, so suppose you have a degeneracy, suppose you have maybe 5 or 7 frequency which are same order, then also will that work?
Well. I mean that is definitely what you are saying makes perfect sense. But again, what I'm saying that comes under, if you looking at that, whenever you are prefixing your p, that means you are automatically making that assumption that there is no degeneracy. That will come under the estimation of the p, because when p because otherwise they are not identifiable. They are not identifiable. So when you say this one that, so all these things what I am saying this one that keeping p fixed. Okay, so that is a completely separate set of problem. I did not want to put it here. That estimation of p, which is also becoming a very important one, where all these things will come into picture. Okay, fine. Yeah, good one, good point. Yes, please. Yes.
In the omega k,
Ha.
are there harmonics?
You can do this one, but it can be changed. But here it is not. Here it is not assuming it. But yes, I mean we can do this one in the harmonic model also. What you are saying, it is absolutely we can do this one, but then you have to change certain things.
Omega k are not harmonics, then the sum need not be deviated at all.
Some need not be, well, I mean that's the reason, that's what I am saying. I mean, see, it is an approximation of the Fourier transformation, of that Fourier expansion. Okay, we are making that approximation, so that means what you are doing it, you are making it sufficiently large p. So given the data set, that's the way I am doing it. Okay, fine, because see, I am not looking at the infinite data set, I am looking at the finite data set. So from there I am making that things. Okay, fine, all right, yeah. So the least square estimator, yeah. So but although the least square estimators are the most, okay, I have some, how many minutes? I have around 10, 15, okay, 15 minutes. Yeah. So although the least square estimators are the most efficient estimators, but what happens in this one that, well, your additive errors, but if there are few outliers in the sense if there are some odd data, I mean even if very few, I mean 1 or 2, even if in a large sample size, if you have a few data, the least square estimators affect significantly. The reason is simple, because you are squaring it, because yt minus that quantity square, so that plays, suppose there are few odd data, because that basically dictates the whole estimator, so that spoils the whole thing. So it is well known that the least square estimators are not robust, in the sense if you have a few outliers, then it becomes they do not perform well. Okay, so that's the reason this one that there are some of the few other alternate one, which is the least absolute deviation and the Huber M. I will just briefly mention that. So least absolute deviation, you can see that instead of the square, you are looking at the absolute value. Okay, you are looking at the absolute value, and actually that makes the problem much more difficult one. Okay, because solving this one is a much more difficult problem. Okay, it looks nice. I mean, yes, I mean they are robust and all these things you know, but it is a much more difficult problem to solve. Same thing with the what we call the Huber M estimator. So instead of the square, you are looking at some other loss function, which is rho of that quantity, and which is basically of this form. Okay, so these are the two alternative one which are behaving like a robust one compared to the previous one. So what alternative can be done? What it is called? Well, I mean, as I said, the implementation becomes a problem one, mainly for the large pre, and not only that. Although in the case of the least square estimators, you have a nice theory which can be developed, but which may not be true in those cases, in these cases. Okay. So that's the reason this one, that one of the thing which came up, which is what we call this one as a weighted least square estimators. So you put some weight. The idea is same. That means that if you see that if there are outliers, which basically means this quantity should be large, I do not want that should affect the estimators, and that's the reason this one, that I am putting a weight function before and I want to shrink it. I want to make it, say for example, if this quantity is large, then I will make this quantity to be small, so that overall it neutralizes the whole thing. Okay, so that is basically the idea which comes. So what I am trying to do, I choose my weight function. I will come back to that, how to that, but you try to minimize this quantity again with respect to the same thing, with respect to the parameters. Okay, we go for a simple one. We go for a simple, for example, polynomial weight functions, and then all the things whatever we have done in case of the least square estimators, which can be implemented here. Okay, fine. So, but it gives a robust estimator. Okay, if I choose my weight function properly, it gives a robust estimator. That's what it is. Okay, so these are the simple conditions what I need for the weight function. It has to be only continuous, and it has to be strictly greater than 0 in the range of 0, 1. Okay, that's the only thing what we have. So this is one of the problem, that how to choose the weight function. So what is being suggested, that well, you take a class of weight functions of the different shapes, okay, and among those you choose that particular one which will give you the minimum residual sum subscribe. Okay, that's a standard way. That's the way you're looking at it here, or the cross validation approach. So let's forget about this one, but that is the popular one. That's what we do. Now let me move this one. I'm just avoiding this one. Now let me just move to that what we are trying to put it here. This is one of the things which are being used now. What is called the chirp one. So as we can see, we call this one as a nearly periodic one. So instead of the frequency model A cosine alpha t and B sine alpha t, what I am saying this one, that there is a what we call as a frequency rate. So this is called the chirp model, which is becoming very, very popular one. So that is there, and that is the general chirp model. So your function is only changing with respect to your frequency rate. Everything else remains same. Same problem, you have to estimate all those parameters, A, B, alpha, beta, here, same thing.
This cos alpha t plus beta t, so these functions are not periodic now.
This function is not periodic. So what we call this one as a nearly periodic. It's a nearly periodic function, and these are the frequency, these are the what we call the frequency rate. You can think this one as that, as if the frequency is changing with time. That's what it is, because if you can take out this t common, changing with time. So you can see that frequency actually changing with time in a linear fashion, alpha plus beta t form. Okay, that's what it is. So frequency is changing with time. So the natural extension of this one, these are the applications what we have. Let's not forget. So we have this one-dimensional extension to the two-dimensional chart model, and one of the example what we have seen, which is in the Newton's rings. Okay, the Newton rings, which has been seen as a two-dimensional chart model. So let's look at that. Traditionally the Newton rings are generated by the reflection of light, blah blah blah, and let me put it the mathematical formulation. The mathematical formulation of the Newton's ring, which is in this form, the intensity, which can be captured through this. That is, apparently in the optical literature, that's what we have seen. This is the one. So our main aim, what I am trying to capture, I am trying to capture your I naught, which is the mean intensity, which is not known. A is the amplitude of the cosine variation of the fringes. Lambda is the intensity of the light wave. R is the radius of curvature, and x naught, y naught is the center of the Newton rings. Okay, so there are two things. One problem is that your center might be known or the center might be unknown. If the center is known, then these are the three quantities I need to estimate. I naught, A and R, and if the center is unknown, the estimate center also this x naught, y naught. So this is the problem what we came across, and so therefore mathematically, if I put it, the mathematical formulation, the same thing, whatever we have done it for the one-dimensional case. If you move to the two-dimensional case, I am taking it to be the the center to be known. So x naught, y naught is known, and if you move the center to be 0 by simple transformations, so what you finally obtain that you have this data ymn, that's what you are observing, the intensity, which is in this form, this plus emn, and the problem remains the same. I am trying to estimate a naught, b naught, and alpha naught, same time. Okay, let me just put the two pictures. This is the Newton rings coming from the original model without the error, and with the error, which is like this. Okay, so basically the noisy picture, that's what you observe. This is the one what you observe. From here, basically you want to extract this particular one. So that is basically the problem. Okay, so from those from the noisy picture, ymn, which is plus noise, additive noise, you want to extract this. There are several methods which has been we have seen in the literature. A fractional Fourier transformation, discrete Fourier transformation, neural network. In fact, there are several other, but only one problem what I have seen in all of those, they have only presented the simulation results. Okay, they have come up with algorithm. As I said, these are all basically meta heuristic algorithm. They come up with an algorithm, they are only proving the simulation results, and the theoretical performances are not possible, are not there. Okay. And nowhere it is there. Not only that, they are not robust also. That means that even if there are very, very few odd noises, okay, they are not able to take care. They are very, very sensitive to the outliers. Okay, so that means we are going back to our the standard one. We are looking at the least square one. Well, I mean, we could do all the theory and all these things, but again the problem here is it is again very, very sensitive to outliers. We are not able to, if there are few odd data, we are not able to, I mean they do not behave very nicely. Okay, so that's the reason that, well, I mean, I think this is one of the important thing. I need the theoretical results. The reason is that because, so this is a very, very you can see this one, the standard deviation of that alpha, which is of the order of n to the power minus 3. So that means theoretically it shows that you should get an very, very accurate estimator. That's what it shows. It's of the order of n to the power minus 3. Okay, so you should get a very accurate estimator. So that means if you come up with any other estimator which is of not that accurate, that means you know that you can improve it. How to improve it, that's a different thing. Okay, but you should know this one, that you should be able to improve it. And actually that's the reason the theoretical results helps us to search for something new. Okay, that's what it is. And yeah, it's a computationally challenging, the least square one. They are not robust, as I said. Very good one. Yes, I mean, absolutely, that if it is a Gaussian error, actually that is the Cramer-Rao law, the least square estimator. Very good. Yes, exactly. I did not want. Yeah, exactly. That is true. Absolutely correct. Yes. In fact, in this particular case, the Cramer-Rao law bound is of the form of 1 by n cube form. And actually, even if your m is not equal to n, that also we can do it. But that's a simpler one. I just put it here. Okay. So now, what we are saying, this one, that well, to go for a robust one, we do the similar thing. We are putting the weight function, which is in a two-dimensional function. Okay, so it's a function from basically 0, 1 cross 0, 1 to r plus. Okay, so it is that's a way similar thing. What we do, we are able to do all the theoretical one. The weighted least square estimators can be obtained by solving a one-dimensional optimization problem. The properties of the weighted least square estimator can be derived under the same set of assumptions what are needed for the least square estimator, and to establish any theoretical properties in any other robust estimator, one needs much stronger assumptions. So that's the way actually it helps us. Okay. Well, this is a numerical one. What shows that if there are outliers, then the weighted least square estimators perform better than the least square estimators, and their performance are very similar to the other robust estimator like LAD and the Huber-M. On the other hand, if there is no outlier, then the weighted least square estimator perform better than the LAD and the Huber-M estimators. Because if there is no outlier, we know that they have to be, the least square estimator are the best one, okay, because they reaches the Cramer-Rao lower bound. if there are no outliers. Okay, and that's what you have seen also. If there are no outliers, the weighted least square estimators, they perform better than the LAD and the Huber M. They perform similar to the least square estimators. Okay, so you can gain in both ways. Again, how to choose the weight functions? We'll go for the same way. We choose a class of different smooth weight functions and choose that particular one which gives you the smallest residual sums of square. One suggestion is that you always keep the constant function as a member of this class, because that gives you the least square estimators. So you are looking at a class where least square estimator is a member, so therefore it can tackle even if there is outlier, even if there is no outlier. Both the things you can tackle at the same time. Okay, so that's the suggestions what we have. Okay, so I think that's it. It's a numerically, that's a future one. It is really, because we have not done any numerically efficient one. It has done in a brute force manner, but I think it can be done. In fact, I was telling her to do that one, Anjali. So the numerically efficient least square estimator, numerically efficient weighted least square estimator, and see another important one. See the very natural common things to do. That well, if you have a two-dimensional problem, why not try to reduce it to one dimension? Okay, you just sum up with one of the rows or one of the columns, but then you lose efficiency. Okay, definitely lose efficiency, but how much efficiency do you lose? Is it worth? Okay, so those things I think can be done both theoretically as well as from the numerically also. Okay, I think with this I'll stop it. Thank you for your attention. Yes. Yes, please. Yeah.
How difficult is it to find the weight functions like TT? What are the generators?
See, that is one thing we are working on, frankly speaking, and it is tricky and not tricky both, in the sense that well, one of the general suggestion is that try to look at different shapes of the weight function, in the sense that, for example, I mean, okay, if you go back that why do you need the weight function? Because the way I need it, because I want to put a less weight where there is an outlier. But if I do not know where is the outlier, okay, so what I do, because it's a 0 by 1, 0 cross 0 by 1, so I put a different weight function in my kitty. Okay, so maybe one weight function where the minimum is half. Another one maybe minimum is maybe say half, 1/4, and things like that. Okay, so I will take a basket of that. So now I do these things, okay, for all the weight, and then I look at the minimum residual sums of square, whichever gives the minimum.
So I think I cannot formulate the question well, but my main point is here that how should I think of in this estimation? How should I think of the outliers? Is it a problem?
Yeah. That's a very important problem. That's a very genuine problem. See, there are very well. I mean, that is still it's an ongoing one in general. Let me put it that way. Not only for this problem. I mean, detecting the outlier. There are few techniques. I mean, there are few plots. That's the way. See, one of the simplest way you can see this one, that what you do all the things. Then what you do, that you plot the residuals, and you see this one, that whether some of them is very large or not. But the natural question comes, how large, how small? Okay, so that is a general question. Okay, so it is an ongoing one, depends on the model. Okay, but there are certain tests. Okay, but they are not 100% proof. Okay.
For example, in physics, when we do StatMech of like small systems, like finite dimension, there in some cases this outliers which we call real events.
Yes, exactly.
Also to give like new physical rules.
Yeah,
Here
sure.
outliers are trying to be suppressed or like
Okay. No. Let me put it that way. I think what you said, it's a very important goal. See, that was precisely what used to happen before. That whenever you see the outlier, you just forget about this one. You just discard that one. But then precisely what you said, that was being ignored. That means it might give you to something else completely. Okay, and so that's the reason that all these outlier technique came into picture. That well, I mean, you do not want to completely suppress that one, but in presence of that, you want to see that how it is going to happen. Okay, so exactly. So you do not want to completely discard those things, because you might lose something. Okay, that is what we are saying. That is precisely, I mean, so if you go back around, say maybe around 30 years back, That's what people used to do. Oh, just forget it because these are all very, very bad observations. But then you might lose some of very important things. Okay. Okay. So, okay. Yes.
The image you showed some rings.
Huh.
So that is like the 2D data or pixel data.
Yes.
So how do we convert this 2D data into one dimension and before the number?
No, I mean, see, the thing is that whatever we have done it with the 2D data itself. So, what I am saying this one, that suppose you want to convert that 2D data to 1D data, in the sense, say for example, it's a YMN, so it's a matrix. Suppose you simply add the rows, okay, so you'll be getting only one column. So you can, that is a one-dimensional data. So suppose you want to work with that, or suppose you want to work individually with the each rows. So these are all 1D data.
But in a 2D frame, it is not a periodic frame because it is symmetrical about the center.
No. So what I am saying this one, that you will be observing at the time point m and n, where your m and n is 1 to up to capital M, n is 1 to up to capital N. That's what you are observing. Okay. Okay. I mean, you are talking about from the picture point of view. No, but the thing is that at the end of the day, I am not looking at the picture. I am looking at the model. I am looking at the data and looking at the model. I am just putting the picture just for the. I mean, how does it look finally? See what I will do eventually. Okay, I will analyze the data. I will get the estimates. And then I will estimate the picture, and then I will put that one. That's what I will be doing it. Is that, did I answer your question or okay? Fine. Yeah. So yeah.
Yeah. Maybe just.
Yeah.
So, like for example, when you have the time series data, like in each bin you will have some certain number of events, right? Some certain number of data points, right? So that defines like your statistical 1 hour square.
No. Let me put it this way. The way this particular data will be. This particular data will be in the form of, say for example, the at each pixel, basically you have a value. What is that value? That value will gives you what you see, because see all this picture are in a two-dimensional one, in the sense the black and white picture, but you can put it in the what they call as a gray picture. So they have a leveling. Leveling for example, say it's a completely white one, say maybe 0. Okay, completely black one might be say 1. Okay, so what we have for each pixel, you have a value.
So can I put it this way?
Yes.
That binning has already been done and you have gotten the data.
Absolutely. Yeah. Oh yeah. So I am working after that. Yes. Everything has been done. I had given you this YMN, which is the binning has been done, and for yes, exactly, absolutely.
Different binning is different.
Absolutely.
Because for different binning, the error can be like voice.
Oh yeah. Definitely. Yeah.
Whatever that way you get, once you get that data.
Exactly. After that you start. After that, whatever I am saying it is starting it after that.
Questions? Last one maybe? There is none, then we just.
Okay. Thank you.